Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. In last sections, we have designed all the members, the beam, columns, rafters, the bracings to safety. Now in these sections, we will learn how to optimize these sections. Now if you right click on the screen window, then go to design result, click on radio button, show diagram. You can see the interaction ratio. The required interaction ratio is usually less than 1, but you can see the interaction ratio at various places is quite low, so we can go for optimization. Now while optimization, we should also keep in mind that there are some practical consideration which are to be looked into. Now let us go to one of the frame and see how the bending moment diagrams of the frame looks like. Let us select a frame, view selected object. Now mode, go to post processing, apply. The load case 51 is there. This is a gravity load case with dead load, live load and all dead load. Click on bending moment diagram MZ icon on the top ribbon. Now you can, in dead load, live load, the bending moment diagram is something like this. Now if you go to envelope, now if you see the bending moment diagram, at one end the bending moment diagram is something like which seems to be a wrong value, because this is the frame is a symmetrical frame and the bending moment diagram at the envelope cannot differ by too much. So let us see in which case the bending moment works out to be 215. Let us go one by one in the load cases. First 51, okay, 86 at 82, that seems to be right. 101, 102, 32, 30, 55, 27, 50, okay, 29, 31, 74, 71, not much difference. 115, see how much is the difference, 115 and low both 116. So in what is the load case in 115? Let us go to the load combination in the editor. Open the editor. Now let us go to load case 115 and 116. See, there is a typographical error. If you can see in defining the load combination, so 11 1.2 12 is equal to 1.2, 6 is equal to seems to be 14. Now this has been a typographical mistake, so we have to edit it. you have to edit this 1.2 and 1.2. So delete 1, so 6 is equal to 0.6 and minus 0.6. Now see, this kind of mistake can happen while defining the load combinations. I actually did it deliberately because many times for fresh engineers or even with experienced engineers, when they define load combinations or load cases, the factors might be provided as a wrong value. So that is why we should be careful while defining the load combination. Even after we should always read the see the bending moment diagram just to find out if the same thing is okay. So we have actually looked into the bending moment diagram here. So from this bending moment diagram, we could work out that there is something wrong. So we are able to find out the reason as well. So let us go to the editor again, let us save it, and now let us give it a run. Now if you go to post-processing, mode post-processing, apply MZ, envelope. Now our bending moment diagram looks fine. So now we'll start optimization of the structure one by one. View whole structure, put up the moment diagram. We shall first select the joist using group name. Select the joist, view, right click, go to level, design result, show diagram. Okay, now you can see the interaction ratio. These interaction ratios are quite low. So let us go to property, change this joist section. Let us make it 212, 130 by 6. Change, yes. Then give it a run analysis. Done. Go to level, design result, show diagram. You can see the interaction ratios have gone up. Now if you go to post-processing, mode post-processing, apply MZ, envelope. Now our bending moment diagram looks fine. So now we'll start optimization of the structure one by one. View whole structure, put up the moment diagram. We shall first select the joist using group name. Select the joist, view, right click, go to level, design result, show diagram. Okay, now you can see the interaction ratio. These interaction ratios are quite low. So let us go to property, change this joist section. Let us make it 212, 130 by 6. Change, yes. Then give it a run analysis. Done. Go to level, design result, show diagram. You can see the interaction ratios have gone up. When the interaction ratios of a simply supported beam reaches or exceed beyond 0.75, we should definitely check the deflection, vertical deflection with respect to the surfaceability. Usually, if the interaction ratios remain below 0.75, the joist or simply supported beam usually satisfies the deflection limit of span by 240. That IS 800-2007 gives deflection with respect to live load only, that, and it doesn't define any deflection limit with respect to dead load plus live load. The reason being that the dead load deflection actually doesn't matter much if the strength of the beam is okay, but for usual practice we limit the deflection under dead load and live load by span by 240, because excessive deflection will produce a psychological fear to the users. When deflection due to dead load is excessive, a consideration to provide camber to the joist or beam should be looked into. So now let us go to mode post processing, apply, click on deflection diagram, go to result, view value, beam result, max resultant, annotate. How to decide whether these deflection limits exceed the permission limits? This deflection limit is the differential deflection limit. Now, what is differential deflection limit? Now, to understand that, we should go to the entire from floor level, view whole structure, so let us select the floor, view. Now see, the maximum deflection is here in this member, 22.806, and length of this member is 4 meter. If we again draw this, take this line, the 4 meter display will be gone. So now if you see, for this beam, for this joist, the deflection at end is, if you draw this beam, deflection at this beam this end is going by 7.352. This beam is going by 7.464, and if you join these 2 points, this will be something like this. So, and the center point is going down by 22.806. So the beam is deflecting like this. Beam is deflecting like this. So this is the differential deflection. This is the difference. So how to compute the differential deflection? So what is the average deflection here? This is equal to 7.352 plus 7.460 divided by 2. This works out to be 7.406. This is the average deflection at the mid span. So what is the differential deflection? Differential deflection will be 22.806 minus 7.406. This is equal to 15.4. Now what is the permissible deflection limit? Span by 240. This is equal to 4000 divided by 240, that is equal to 16.67 mm. So note, see, with the interaction ratio of 0.9, the deflection is almost reaching the permissible limit. The differential deflection is 15.4 mm, while the permissible limit is 16.67. So that is why I say whenever the interaction ratios exceed 0.75, we definitely must check the deflection of the beam, whether it is within limit or not. But it is better to make it a usual practice to check the deflection of all the beams, whether the interaction ratios are lesser than 0.75 or it's more than 0.75. Now let us go back to the sizes of the joist which will be usually feasible in a plant. So that we had defined as 212 and 130 by 6. Change. We have to give a run to the frame before going to the model, before going to the frame by frame optimization. So let us give it a run. Done. Now go to view whole structure, go to top view. Let us first select the two critical frame. View, selected object. Now let us see what is the interaction ratio here. You can see there is lot of scope of optimization. So 0.349, 0.408, R15 is 0.408, 0.397, 0.369. So the frame members R20, R12, the interaction ratios are quite low. So go to property. Let us see. Let us reduce all these sizes. What are the sizes? Let us note down. This is, we can think of reducing R17, R15, R14, R12 as well as R20. So what is the interaction ratios of R17? Is 0.365 is maximum. R15 the interaction ratio is maximum is 0.4 408. R14, the interaction ratio is maximum is 0.369. R12, the maximum interaction ratio is 0.519. R20, the maximum ratio is 0.58. Now let us go to R14. We have 374, 005, 175 by 12. Let us change it to 366, 175 by 008. Change. Yes, post processing result is gone. Then R15, we have 424, 005 by 225 by 12. Let us make it 420, 420.2010. Change. Then R15, then R17. Let us make it 0.42, 0.416, 0.416, 0.15, 0.008. Change. Then R12, edit 0.37, 0.175, 0.01. Let us make it 0.15 and 0.01. Change. Then R20, let us make this also 0.15. Change. So now let us give it a run. Run analysis, save. Done. Let us see the interaction ratio level, design result, show diagram. See, the beam number R12, we have to increase the flange sizes, but the R14 and R15 has still got a scope of optimization. Then R17 also still has got optimization. So let us note down the interaction ratio again. So these are the interaction ratio. Now let us change one by one. R12 we have to increase the flange height or depth. So let us make it 175 by 10. Change. Yes. Then R14 we have maximum 525. So we can reduce this R14 considerably. So let us make it 0.15, 0.008. Change. Then R15 also quite, so we can make it 370, so that or both the frame remains same. So 370 by 1.15, 0.001. Change. And then we have R20 as 0.75. R20, edit R20. So let us make this 0.316.15.008. Change. So done. Let us see the interaction ratio, level, design result, show diagram. See, our R15 is not okay. So let us change R15 again. R15. Let us make it 0.175. Change. Some splices here at this position, say at 1.3 times of the height of this column, and think of further optimization. But for this kind of height, usually splice is not provided in a building, but for the sake of understanding, we will consider that we are providing a splice connection in this column at these points. So let us measure the size of this column. Let us height of this column. This is 3.88. So 3.88 divided by 3 is equal to 1.29. So let us introduce sections. A node at 1.3 meter, add 1.3 meter. Okay. Now see, we must remember that whether we have provided LX, LI or LZ parameter of this member or not. For this member, we have kept the node to node distance as default parameter for LX, LI. Now since we have introduced a node here, so we must define the LX and LI parameter of this. So this LX and LI parameter will be 3.88. Let us go to general, design, parameter, define parameter, after current, LI is equal to 3.88 because it is braced through concentric bracing in about the minor direction. So LI, okay, we have to select a command just before check code, then define parameter R, select the beams, define parameter LI 3.88, assign, and LX 3.88. Let us select the members LI, LX, define parameter, after current. We have to select a parameter just before the check code, then only the after current will function. So let us provide alloy as 3.88 because effective length factor will be 1 about minor direction, because minor direction is braced with the concentric braces. So assign Lx will be 3.88 because the fixed connection will provide torsional restraint. So assign. See, I have selected the upper current. So now if you go to the Lx and Ly has been assigned. So for these two columns, Lx and Ly has been already provided as at 1.5. So we need not require to define them again. Now let us give a run analysis, save. Let us see the interaction ratio after the analysis and design is done. Level, go to level, design result, show diagram. Now see, this column doesn't have a possibility of any optimization because it's 0.8 and 0.77 is at the top. So for the sake of example, we will design a splice connection here. For this column also, the top part is critical, the bottom part we have already taken minimum sizes, so we could reduce the size of the flange, but for a column it is better not, we do not reduce the flange width by lesser than 150 mm. So, and it is always better to have wave depth of uniform depth at top and bottom, so that the axial load that is being transferred to the column below is not eccentric. Otherwise we have to apply eccentric movement if we changes the wave depth of different columns. So in the next we will see how we can optimize the Raptor. Our Raptor is a uniform section now. So this is 262, this is okay, 416. So the Raptor has still got a possibility of optimization. Let us first see what could be the possible optimization, then we will make it a taper section. So R17, we have 416 on 50 by 00. So let us make it 366. Okay, let us make it 4 mm. Let us see what happens. Run analysis. Done. Right click, level, design result, show diagram. Okay. So the interaction ratio is 0.754, 0.725. So there is still a scope of optimization, but we shall not optimize this further because we will define this Raptor as a tapered section. So in tapered section, what happens? We have a column. We have a column like this, flange, and then there is a connection plate, and the tapered section goes like this. Now from the correction, further the correction, the depth of the sections reduces. So this beam column joint attracts more forces. There is the bending moment at this point will be more than what was there for a uniform section. So that is why we are not going to reduce the section depth here, uniform section depth, and we will define tapered section with this section itself. We have column depth as 366 here, 376, 370. For all practical purpose we shall treat both of them as total 370 mm. So this is 370 mm. This distance is 3.105. Then this will be our minus 370 divided by 2, 2830. So we need to introduce on node so that our total depth become total piece of length becomes 4500 in multiple of 1.5 meters, so that plate weight is minimum. Plates are usually available in multiple of 1.5 meters. So 454,500 minus 2830 is equal to 1670 mm, that is 1.67 meter. So we shall introduce node here at a distance. Insert node on 0.67. okay, post processing result will be gone. So this is our total distance now, 4.6. so 4685 minus 370 by 2 is equal to 4685 minus 370 by 2 is equal to 4500. So now we shall have sections something like this. This will be our column, and there will be connection plate here. Tapered section, and this goes like this as per the slope of the roof. Then a section like this. Again this goes like this. Connection plate. So this is our 4500. This will be our 4500, and this will be balance, which shall be worked out during the preparation of shop drawing or fabrication drawings. So at 3.105 there is a node. So actual distance is 2.83 to this point. This is 2830, and balance is 1670. 70. So we have a triangle like this. At far end we will have a depth of 366. Here we will have a depth of 266. This is a triangle. So this is 100 mm, this part. So what will be the depth here? You have to compute. So 100 divided by 4500 into 1670 is equal to 37 mm. So total depth here will be 266 plus 37 is equal to 266 plus 37 is equal to 303. So at this point total depth will be 303. At this point 266. At this point 366. At this point we will again have 366. So in STAAD, when we define a tapered section, the start node shall have a getter depth. So let us see the incidence of member where the starts and ends are there. Press Shift T. For this start is here, this is okay, this start is here, For this part will be lesser depth here, so let us redefine it. Tool, redefine incidence, switch incidence. So now the middle part will has getter depth, so this is okay. Again this will have to switch the start and end of the member. Geometry, tool, redefine incidence, switch incidence. So now see, if we do not do these things, the start pro many times gives wrong results. So we have to always ensure that the start depth of tapered member should have getter depth, and the end depth of tapered member should have lesser depth. So let us now define the sections. General property, let us off it. Define tapered eye 0.366, 0.004, 0.301 we had calculated, then 0.15, 0.008. This is our first section. Then 0.301, then 266. This is our second depth. Then again 366 and 266. Now let us try with lesser depth, 0.13, 0.006. Let us make it 262 and 362. So the wave depth remains as 250 at the connection plate end, that is at this point the wave depth shall be 250 mm. So let us add this section as well. Add. Now let us assign all these sections. 1, 2, 3, 4. Assign. Then let us assign this one. 1, 2, 3, 4. Assign. Then let us assign this one. 1, 2, 3, 4. Assign. Now let us now see the 3D view of this so that we know whether the assignments are correct or not. View 3D. See the probably the start and end depth are not okay or I have. So let us see. This is start depth. This is start depth. So 362 to 62 start depth. These two members, the incidents are not okay. If you see, we had defined it, but it did not change for some reason. Let us again redefine and switch incident. So this is start. Now let us see the section depth again. Go to 3D view. This is start. This is not okay. Why? This is start. Okay. This should be also redefined. Tool. Redefine incidents. Switch incidents. Now again let us select this. View, sorry, 3D view. So our sections and start and end incidents are properly defined now. So let us press shift E. Now let us give it a run analysis, save, done. Let us see the interaction ratio label, design result, show diagram. Apply, okay. See the consequence of redefining the sections of the reactor. This has become blue 0.99. So we will redefine this as 15, member number 15 itself. So let us make it 15, assign, yes, run analysis. Now the see the interaction ratio. This is how we should go frame by frame and optimize the sections. So now I will show you longitudinal section. What is the possibility? Let us go to view, whole structure. Let us see the end frames, longitudinal frames. View. To see the starts, 114. This is 100, 104. These have possibilities of. And then see these 5 sections, so we can reduce all of them. R8. So let us see the cylinders ratio requirement also. 143 to 250 is the minimum for this. 102, so still we can redefine. So let us redefine R6 as nominal bore 82. So 82 will become 88.9. 4 as medium sections. Change Then R2, what is R2? R2 of 1, so we will make it 88.94, that is with nominal bore. And R5 we can make it 91.3.6 change. Then R8 also we can make it 91.5 3.6. We shall not reduce because beyond this, because this amount of surface will be required to hold infill walls. Assign. Then let us go to R18, edit. Let us define this as a (114) medium sections. Assign. So you can take Indian sections or Tata structure sections, any of them will do. So let us give it a run and see what happens. Run analysis. Level. Design result, show diagram. Okay, apply. Now see. So we can still reduce these bracing members, this one and this one. So this is R18. Let us make it 88.9 medium, change. Yes. One beam has been left as standard section by mistake. We should change that as well. Let us see what can be assigned. So let us assign R10 to it. Run analysis. Done. Label. Design result, show diagram. Apply. OK. Now see the ratio of this has become quite high, 0.97. So we should actually go back to 114 itself with nominal bore 100 mm, because 0.9 is very close to 1. 0.99 is 0.97 is very close to 1. So let us redefine it. (114) change. Yes. Now see the interaction ratio. This beam we can further optimize. 316 008 150 501. This will not reduce lesser than, so R9. Let us go to the floor plan again. View, whole structure. Let us try the R9 with R8. Assign yes, and R2 was showing getter ratio, so let us assign R2 as 114. Run analysis, save. Label, design result, show diagram, apply. So R8 is not okay, so we have to go back to R9 only. So let us make it R9 on again. Assign, run analysis. So after trying with R9, we have these results. Now let us go to view whole structures. R15. Let us make R15 as a uniform sections of 200 depth and at the gable end, and see the results. Define. Let us change gable end beam on the cantilever beam to 200 depth member. So 0.262, 0.004, 0.262, 0.13, 0.006. Assign. Okay. Let us give it a run. Run analysis. Done. Label, design result, show diagram, apply. Okay. So this is working. So now I have to still check, last check, select by specification, failed beam, no beam failed or still design calculation. Okay. So with this, our optimization is more or less done. In next sections, we'll go through the dynamic analysis part again, where we will change the scale of the response spectra so that we can match it with the base shear of static base shear that has been obtained from static analysis, static seismic analysis. And then if any member fails, we shall resize them to safety, and thereafter we will check all the serviceability requirement, that is with respect to the lateral deflection for seismic cases, then lateral deflection for wind cases, the story drift, and then the vertical deflections or vertical displacement with respect to the serviceability requirements. So let us see you in the next section.